The Mona Lisa operates as a highly engineered physical system. To understand its function, we have to look past the historical baggage and focus on the literal surface of the artifact. Every element of the portrait can be deconstructed through the rigid laws of structural and optical physics. Analyzing the portrait requires a precise intersection of four specific disciplines: structural mechanics, organic chemistry, optical physics, and cognitive neurobiology. We will follow the construction of this object from its base substrate up to the viewer's retina, utilizing data mapped by modern particle accelerators. These four sequential layers define the physiological and physical mechanics of the world's most scrutinized image. The foundation of the system is a single flat sawn panel of white poplar, Populus alba L. This wood exhibits anisotropic properties, meaning it expands and contracts at different rates in different directions. Its tangential expansion rate is significantly greater than its radial or longitudinal expansion. Because the painted front face is sealed, moisture can only enter or leave through the unpainted back. This creates a permanent moisture gradient, causing the panel to warp into a double curvature with an 11 mm cupping deflection. Internal transverse tensile stresses eventually caused a 110 mm crack along the radial plane. This fracture occurred when an early rigid frame restricted the wood's natural movement as it dried. Today, conservators monitor the panel's flexural rigidity using load cells and custom sensors known as jocondometers. These instruments measure the exact forces the wood exerts against its frame in real time. The panel exists in a state of perpetual structural tension, operating as an active mechanical system. To prepare this volatile poplar surface, Leonardo needed to chemically seal the uneven wood grain. In 2023, researchers at the European Synchrotron Radiation Facility analyzed microscopic samples of the undercoat. They detected an unusual and highly unstable chemical lead compound that does not occur naturally in typical Renaissance pigments. Leonardo synthesized this layer by dissolving litharge, a lead oxide, directly into hot drying oil to act as a powerful ciccative catalyst. This chemical reaction produced plumbonocrite. The compound accelerated the cross-linking polymerization of the oil, allowing the layer to harden quickly. It thoroughly filled the wood grain and created a perfectly smooth, stable barrier. This deliberate chemical synthesis provided the reflective, durable foundation required for the complex optical physics of the upper layers. On the surface, the sfumato technique creates deep shadows without sharp outlines or visible brushstrokes. Scientists used quantitative X-ray fluorescence, or XRF, spectroscopy to map the physical structure of these shadows without touching the painting. The process relies on differential absorption. High-energy PBL lines at approximately 10.5 kiloelectron volts pass through the upper organic glazes without being absorbed. However, lower-energy PBM lines are heavily absorbed by the atoms in the overlying glaze. By measuring this attenuation, researchers can calculate the exact thickness of the paint. These measurements reveal that the shadows are built from 20 to 30 superimposed layers of glaze. Each individual layer is only 1 to 2 micrometers thick, doped with precise amounts of manganese and iron oxides to control the absorption of light. Sfumato acts as an opt-off filter, selectively absorbing light photons across microscopic depth gradients. Once light leaves the canvas, its effect is determined by the neurobiology of the viewer's retina. Foveal vision is centered on the fovea centralis. It is optimized for high spatial frequencies, resolving fine details and sharp boundaries. Peripheral vision, by contrast, processes low spatial frequencies. It resolves blurry features, shadows, and broad gradients rather than exact lines. The sfumato around the mouth is engineered to fall within this low spatial frequency range. It lacks the sharp boundaries foveal vision requires to resolve a static shape. When a human viewer gazes directly at the eyes, their peripheral vision picks up the soft shadows of the mouth, which appear to curve upward into a smile. Looking directly at the mouth engages foveal vision, which resolves the neutral structural details and erases the expression. Saccade contingent display experiments confirm this neurological effect. Changes made to a face during eye movement, when the brain temporarily stops processing visual input, measurably alter the viewer's psychological perception. The changing expression is a biological illusion, exploiting the anatomical divide between the pathways of human visual processing. From the retina back to the core, the system moves from neural frequency channels through 20 glaze layers, past a sympathized plumbonic barrier, and into the fibrous grain of anisotropic wood. Building this artifact required chemistry, maintaining it requires structural engineering, and viewing it requires physics. Preserving such an interconnected system requires arresting its thermodynamics entirely. The airtight Gaupion vitrine maintains a constant 21 degrees Celsius and 50% relative humidity to stabilize the mechanics of the panel and the chemistry of the paint. Leonardo da Vinci's methodology integrated the study of nature and the human body so thoroughly that modern particle accelerators and neuroscience are required to fully understand the result.